Hello class. So on this video, we'll do an example of damped motion, when we have damping forces on the object. In the previous video, we saw an example of the three cases, right, where we get either over-damped, under-damped, or critically damped systems, right? So I show you in Mathematica what that looks like, and then how the solutions would look like for those particular cases, right? And now we're just going to work in examples. So we know how to set up the differential equation and basically interpret it. After this example, we're going to go over a quick example or a quick idea of how forced motion works. And remember, in this case, we're still assuming free vibrations, right, or oscillations. And then I'll ask you more about that in the next homework, about forced motion. Okay. So let's start. Example 3. A 1 kilogram mass is attached to a spring whose constant is 16 newtons per meter. Right? And if you remember what I said, the units for the constant don't really matter. You can always find them, right, by dividing in the equation for when you set the weight equal to the restoration force. When you solve for K, you can divide by all the units, and you can see what the unit is. But for our purposes, it doesn't matter, right? As long as all the units match and you know what they are, it doesn't matter what K is in terms of the units. All you're interested in is the actual value. Okay? The entire system is then submerged in a liquid that imparts a damping force numerically equal to 10 times the instantaneous velocity. Right? So our beta, right, and our proportionality constant for the damping force in this case would be 10. Okay? Determine the equation of motion if, and there's two cases. I'm just going to do part A, and then you can do part B as an exercise. So the mass is initially released from rest from a point 1 meter below the equilibrium position. Then, even though we're not going to do part B, that part B says the mass is initially released from a point 1 meter below the equilibrium position with an upward velocity of 12 meters per second. So let's start. So we know what our differential equation looks like. Right? That's the first thing. So let's go to a new page. We have x double prime plus beta over m, because remember we divide by the mass, x prime plus k over m x equals 0. Right? That's always a system when we don't have any forcing vibrations. Right? So when we're working with free vibrations and including damping, this is the system you get. Okay? Now we have some information. The mass m is 1 kilograms. The K is 16 and beta is 10. So let's write all of that out. So the information that we have. If you remember in the example we did in the previous videos, we have to find all of this, right? So beta I'm always going to give you because there's no way to find it, but you could be asked to find K like we did in the previous video. Right? But in this case, I give you everything. And also, if you notice, I already give you the right units for everything. Right? I give you everything in kilograms, everything in newtons, right? So we can use so we don't really have to do anything in terms of changing the units. Right? They already all match. Right? But again, if they don't match, you need to make sure that all of the units match. Okay? So M was 1, K was 16, and beta was 10. So if we plug all of this into our ODE, we get x double prime plus 10x prime plus 16x equals 0. Now, we also have initial conditions, right? Remember, we're in part A. So what are the initial conditions for part A? The mass is initially released from rest from a point 1 meter below the equilibrium position. Remember, when we're below equilibrium, that means positive. Right? And it's just released, right? So released from rest, so we're not giving it any push or pull when we release it, meaning that the initial velocity is 0. Let's go ahead and write that. Actually, let's write it up here. So we have x of 0, its initial position is 1 meter below equilibrium, right? So it's positive 1. And that initial velocity, we release from rest. We don't give it any pull or push. So this is going to be 0. Okay. So now let's go ahead and find the general solution for this ODE. And then we'll worry about the initial conditions. Right? So it's constant coefficient, second order linear. So as you know, we need the characteristic polynomial. Let's use a different color, which in this case is r squared plus 10r plus 16 equals 0. Now, is this going to factor nicely? 16 has factors 4 and 4, 8 and 2. Yeah, it does factor nicely, I think. Okay. So if we set it equal to 0, which I already did, I think this factors as 8 plus 2 and then r plus 8, sorry. Okay, so we're in the case of two real distinct roots, right? Which means that we're not going to get any oscillation. Right? So this would be the case where we are overdamped, right? The damping force is too large, which causes the system to not have any oscillations at all. So from this, we can just read the solution, right? We know what the roots are. R equals -2, R equals -8. Right? So what do we get? We get a solution of general solution, right? Let me do sub C. So in the previous video, I think or a couple of videos ago, I was writing Y, and I mentioned, oh, I'm still used to writing Y. So the variable is X, and I'm writing X sub C to say that this is just a complementary solution. It's a general solution. It's not taking into consideration the initial conditions. So we know what the roots are. So just put the roots in the exponent. Now, let's deal with the initial conditions. Right? The first one is x of 0 equals 1. Let's just go ahead and do that. Right? So what's x of 0? Plug in 0 everywhere. I get C1. Oops. X of 0 equals C1 e to the -2 times 0 plus E2 e to the -8 times 0, which is all equal to, so 0 in the exponent means everything goes to 1, so we get C1 times 1 plus C2, and we know this has to be equal to 1. Now, let's find, and this is the part we're interested in. Now let's find the second initial condition, right? Being that its initial velocity is 0. And so we need x prime, so let's find that first. Okay, so this is going to be -2c1 e to the -2t minus 8c2 e to the -8t. Now, we know that when we plug in 0, we should get 1. So let's see what that looks like. Okay, so again, e to the 0 is just 1. So I'm just going to skip some steps and write -2c1 minus 8c2. And this should be equal to 0. So what do we have? We have two equations and two unknowns, so we can solve. So our system of linear equations is C1 plus C2 equals 1, -2C1 minus 8C2 equals 0. You can solve for one variable in one equation and plug it into the other. So let's say we solve for C1 in terms of C2. So this implies C1 equals 1 minus C2. Plug it in. So we get -2. C1 is 1 minus C2 minus 8C2 equals 0. Let's simplify. -2 plus 2C2 minus 8C2 equals 0. So add 2 to both sides, combine 2C2 minus 8C2, and we get -6C2 equals 2, which implies C2 equals -1/3. Just divide by -6 on both sides. From this, we can find C1, right? Because we know that C1 is 1 minus C2. Right? 1 minus C2, which is 1 minus 1/3. Sorry, 1 minus -1/3. Right? That's 1 plus 1/3. Right? So that's 4/3. And then our specific solution, or the solution for this particular system, given the initial conditions, is, so C1 was 4/3. And C2 was -1/3, so minus 1/3. And again, you see there's no oscillations, and this is basically going to be going to 0 very fast, right? Because we have negatives in the numerator, in the exponent of the exponentials. Now, that's the part A. Again, you can do part B on your own. Just the only thing that changes is, let's see what changes. Yeah, the only thing that changes is the initial condition on velocity, right? So now x prime of 0 equals 12. So you can do that. Let me mention something. Let's say we're in the case of when we get two complex roots, right? So we do get oscillations. So let me just mention something about this. So two distinct complex roots. Right. Now, if we go back to, let me see, to what the roots would be, right? So this is what our roots would be, are, if we write it in terms of lambda and w, which again, you don't have to, as you see in this example that we just did, I didn't write anything in terms of lambda and w, right? I just worked in terms of beta, k, and m, which is fine. However, this is going to be useful for what I'm going to write right now. This is going to make things faster. Okay, so remembering that the roots look like r equals negative lambda plus or minus square root of lambda squared plus minus w squared. Right. Where we know what all of this is, right, where lambda equals beta over 2m and w equals the square root of k over m. Right. So this is in general, right? But I want to focus specifically on the case of two complex roots, two distinct complex roots. So we know that in this case, it's equivalent to saying that lambda squared minus w squared is less than 0, right? So we get an imaginary part. And let's read off what this would be. So let's give things names, right? So r is going to be negative lambda plus or minus something times I, right? Because we know that lambda squared minus w squared is less than 0, right? So we know that that's going to be some negative number, and we can just remove I, and we're going to get the square root of something, right? So let's say it's, I don't want to call it w, let's call it, what variable can I use? Let's use b. In general, this is what our roots will look like. Now, let me say something. Right? We know what the general solution is going to be, right? Just from these being the roots. Right? Without worrying about initial conditions, we know that, so just the general solution is going to be C1 e to the minus lambda t cosine of bt plus C2 e to the minus lambda t sine of bt, right? And if you remember the example we saw in Mathematica, it looked like this, right? In Mathematica, all they did was factor out the exponential. So one thing I want to mention is, in this particular case, even though we do get oscillations, right? Because we have cosine and sine, so we know there are some oscillations going on, and we have some amplitude. Another thing you can say is that even though the oscillations happen, this still is going to be going to 0. Why is it going to be going to 0? Well, first of all, what's lambda? So lambda is beta over 2m, right? So lambda is always positive, meaning that negative lambda is negative. Right? So in here we have an exponential, right, with a negative exponent. So we know that this thing is going to 0 very fast. So if you were to take the limit as t approaches infinity of x sub c of t of this solution, this would be going to 0 because of the exponential. This would be going to 0. So this is still going to 0. Right? So even though we get oscillations, those oscillations eventually stop. Unless, and this is the thing I wanted to point out, so this is the case unless lambda equals 0. Why? Because if lambda equals 0, right, which means that if lambda equals 0, beta equals 0, which means that there is no damping. Right? So if lambda equals 0, then we know what the solution looks like. It's going to look like, so e to the 0 is just 1. So we're back to the solution in the case of no damping, right? When there are no damping forces. Oops. And as we saw, in this case, we do get infinite oscillations with a given amplitude. Right? So if you remember, you can rewrite this as a sine of, I think it was Wt minus phi or plus phi. let's say plus, right? So one of them was plus and the other one was minus, where if you're working with cosine, you had a minus. So in this case, you do have an amplitude, so your solutions are always going to be bouncing between some two values, right? Whatever the amplitude is. So they're going to be bouncing between positive A and negative A. So if I were to draw a graph of that, we'd have, so let's say positive A is here, negative A is here, right? And determining the initial conditions, right? This might look some certain way, but eventually what's going to happen, let's say we start down here, but eventually it should start bouncing infinitely between A and negative A. Right? So what I'm trying to say, although I already wrote everything, is that even though when we have damping, even though we still have oscillations, since we're still losing energy, remember that's what damping is. Damping means that there are some forces that are making our system lose energy. Even though we do get oscillations, those oscillations eventually still give off. They still eventually go to zero because we have damping. So the energy, all of the energy is eventually lost. Because remember, the system starts with finite energy. Right? Basically, you pull on the system, you're given a potential energy, you let go, and you have active or kinetic energy, but that energy is eventually all lost because of the damping. So even though you do get oscillations, the solution still eventually goes to zero, as we see from this limit. Yes, and all I'm doing here is doing some analysis on the solutions, which is important, right? Whenever you get solutions to an ODE that you're using to model something, it's important for you to understand what the solutions do. In particular, questions like this, like what happens as T becomes very large? Do we get oscillations? If we don't get oscillations, why? Well, because we have a damping force that's making the energy in the system be lost until it reaches zero energy. So things like that are important to know. Okay, so that's this example. And again, you can do part B later. It's just, oh, let's change this to initial condition. But if you see, it's very easy because we know how to get the solutions. Right? Now, I could ask you things like, now that we found the solution in this case, so down here, I could ask you, was this system overdamped, underdamped, or critically damped? In this case, you would say the system was overdamped or is overdamped. So make sure that you know how to interpret all of this, right? So I could ask you questions like this in the homework, but I also want you to interpret what is going on. So in the next video, we're going to talk about the last assumption, which is free vibrations. Right? That's what we were assuming in the two previous examples. Now we're going to see what happens if we force oscillations on the system. Okay? So we're going to see that in the next video.